checking it out. And for that, you're going to get some real treats today, starting off with one of Tony's longtime friends, Paul Beame, at University of Washington.
Hi, it's just wonderful to be here and celebrate Toni. It's been amazing. And so when I think about Toni, inspiration is definitely the word that comes to mind. So that's just, Toni has been just so much of an inspiration for so many things for me. So anyway, that's what I'm going to talk about. So we shared Steve Cook as an advisor, but it actually took us nearly 4 years to meet. So at Stock 1991, I was at a lunch table with Stephen Bell and Toni, and he told me about this upcoming paper that he had with Toni. Toni wasn't there, and Alistair Urquhart that had produced these explicit pigeonhole principle bounds for constant depth circuits and extended and improving a paper by I-type with I delta 0 bounds. I had no idea what that actually meant because I was really in awe. I had actually spent a lot of time trying to read that paper by I-type. And had been I had actually been stuck. There was a paper 5 years earlier on connectivity, small distance connectivity, that I had spent a bunch of time starting when I was a postdoc trying to read, and I had gotten part of the way, and then I had gotten stuff. But anyway, I found this particular paper like completely incomprehensible, despite trying multiple times. Just I thought I knew something about switching limit and things, and anyway. So, so when I asked Stephen for more, he promised to send the paper, but begged off on more details and said that I really need to meet and talk with Toni. And I think he tried to connect it, but I don't actually remember seeing you at the conference at all, because it was in New Orleans. You were there. And he was saying, well, you've got to meet Toni, but just it was like on day 2 or 3, and we didn't end up meeting at all. So, fast forward. So actually, we were there at that conference with Anne and my daughter Catherine. It was a fun time. She just learned to crawl the first night we were there in the hotel room. Wonderful, wonderful food with her falling asleep on my lap in New Orleans. Anyway, it was a wonderful time. But anyway, so she was just under 1, and we arranged so she'd get a chance to spend time with her grandparents in Toronto, and it was really going to be great. So I would be able to be in Toronto. I could actually go to U of T to work, so that's how we could justify, the extended time in the summer in some sense. So it ended up being just a truly momentous summer. So with this paper in hand, Stephen had sent me a copy. I finally felt I was starting to understand things and was really excited to meet Toni and learn more. But when I arrived, Toni was away and Steve Cook was in Prague. However, Russell and Pagliazzo, who I'd seen it at a distance, but I hadn't really previously met, was there. And I think Jeff Edmonds introduced us. They were hanging out in the area just in front of Steve's office, and began talking about connectivity and switching lemmas. And Russell and I particularly were talking about, what I could understand, what I understood, and I-type's earlier paper. So we worked for a bit. And I was really focused on connectivity, but the connectivity part didn't work at all. But things were seeming promising that there was something, but we really, at least I didn't really understand what was going on. But after Toni arrived and I finally met Toni, Toni explained the framework, and there was a lot of back and forth going through the ideas. And it wasn't actually that long before we were excitedly celebrating together. So yes, as you heard last night, there were some hiccups along the way a little afterwards, but anyway, we were happy pigeons. So anyway, so that was the start, and somehow, I mean, for me, it really has, that was a start. That was something that was really life-changing, and somehow just things seemed to click. And by far, more of my work has been with Toni than with anybody else. And we could, we were in different parts. I was in Seattle, Toni was in Toronto, in San Diego, and Pittsburgh, in Arizona, back to Toronto, sometimes at IF. Anyway, so we would only see each other maybe a couple, 2 or 3, maybe 4 short times a year with different time zones. We emailed constantly. So in 1993, 94, I had my first sabbatical in Toronto, so nearby family. Toni was a postdoc at UCSD. I spent more time emailing with Toni than I did with talking with anybody at Toronto, actually, for that year. And basically, after that, we periodically, there was email, but we had to have these long phone conversations, and we'd talk, and that phone conversation, that was the start of, would be the start of a new project, and we're back email again. But that was kind of, those conversations were really just a huge inspiration. And I went and looked. So I used to sort my mail between 1991 and 2005. There are over 2,600 email messages from Toni. I don't have the record of my messages to Toni from that time period because I didn't save sent mail, but this is what it was like. Yeah, I should have, I did occasionally. Anyway, I was not. Yes, so anyway, so here are some of the papers that we worked on together, in kind of sequence, and it varies. There's even some work on actual, practical systems for component caching, random things that we ended up working component caching together. Oh, stabbing planes. Yeah, sorry about the name. I think I came up with that name, but Noah was kind of disparaging of the name yesterday. So, so anyway. But we didn't always have the best of, most exciting range of titles. So I did the word thing for all of our papers, and this kind of was what I came up with. Anyway, so there's so much to talk about, and looking at the emails, some of these were overlapping. Like it was like particularly some of the early ones, there would be multiple things at once, and so messages on different papers were because so much was happening. Particularly early on. Anyway, so this was really just anyway, it's just been amazing working with Toni, talking with Toni, and you've really been inspirational for me. You really, I mean, you'll always have the eyes on the prize, the big questions, right? You're never willing to settle for superficial understanding. Like Toni has this way of saying, well, I don't really understand something, when she understands something at the level that lots of the rest of us understand things, but not at the level that she really, really wants to understand things. And this is just, I can look at them, I did a little look at some of these messages, and some of them are, well, yeah, but there would be, but we really need to, go further, go deeper. Isn't there another better way to think about something? And you are always ready to challenge assumptions and just have this amazing ability to make connections between different things that you've been thinking about, other people have been thinking about, that you've heard about and just brought together. It's really, and most of all, in a lot of ways, personal research, everything, you just make everybody around you just better. So speaking of inspiration, I thought I'd talk a little bit about some recent research with Sajin that was inspired by Toni, but not with Toni. We can always work on that. We had this paper on Lovaas, Scriver, and beyond in the mid-2000s. And we proved a very specialized kind of lifting with AND gates to multi-party communication complexity. And I know at the time, again, Toni, Toni realized that there was so much more than this. And you all know, and Toni and just an absolutely amazing collection of grad students and co-authors have done, produced this phenomenal range of query to communication lifting results. And again, speaking of being in awe, we can all sing the song that Russell wrote the lyrics to on Monday to think about all the different ways that this work has changed the field. So actually, I don't know that anybody has technically, talked technical things about lifting, so I'll do a little bit. So in general, a number of these results, the first results almost always talk about this index gadget. So for lifting, so I realize I don't actually have a picture of this composition, but anyway, you have some function and you have a gadget called the index gadget where Alice has a pointer X and Bob has a long string Y, and the goal is to output the bit of Y pointed to by X. And so the general idea, I can't believe I left off the picture. Let me actually draw it for like the one or two people watching online who may not have seen this. So you're plugging in, you've got your function Z, Z1 through Zn, and you have the inputs to the new function is a function of bits x1 and y1, or a vector x of inputs x and y, and that's the gadget. So and the goal is to show that the communication of this problem, this combined problem, is large if the decision tree complexity of F is large. All right, so the typical and Toni has conjectured that constant size index gadgets are enough.
I've changed my mind.
Yes, I understand you might have changed your mind. I know you can do, but yeah. So anyway, well, it's okay, but hey, we wanted to try to prove something on this, so that was our inspiration. Yeah, yes. And so how do these query to communication lifting theorems work? So this is what I mean by, that picture is what I mean by F composed with G, where G is the index gadget, and this is the decision tree complexity of F, and that's the communication complexity of G. But since we're dealing with constant, so anyway, so the general paradigm for these proofs is to design, and this general paradigm actually goes back to work by Roz and Mackenzie, and Pierre's Pierre's here as well, is to say that if you have a protocol from F for F composed with G, you can get a decision tree for F where you might not have to use, you could even save the communication complexity of G in it. For this purpose, for our purpose today, G's only a constant number of bits, so we might as well just think of this as one. So anyway, so the input is a protocol that solves F composed with G, and the output is going to be a decision tree for F. And so here's the picture. We've got our protocol pi solving F composed with G, and we want to produce a decision tree. So what we'll look at what's going on in the protocol until we get a point where we've got too much input information about some pair. So we query that that input to F because we've got too much information about what's at the bottom. So that tells us too much about Z potentially. And then the decision tree, so we have to branch on both of those possibilities, and then we figure out some more in the protocol, communication protocol. We get too much information about another input pair, and we query that, and so on. And then at the bottom, when let's say the function produces output ELF in the protocol tree, the decision tree outputs L. And very importantly, not in this picture, this also works for relations like the clause search problem, which you've heard something about a lot about earlier in the program. So so that's the simulation, and so in general, one maintains some simulation invariance. So since it's a communication problem, there's a set of inputs, which is the vector of x's, and a set of, or a subset of the set of x's, vector x's, and a set y of inputs that are currently consistent in the protocol. There's a set of fixed coordinates where the decision trees has queried the answers for all of those fixed coordinates, and you've maintained the invariant that all of these pairs of inputs are consistent with that set of Z values. And there's the key thing in order to be able to continue the simulation is we need something which is a disperser property. The simulation must be able to produce all possible future query answers on the remaining coordinates, one of the ones you haven't looked at. And maintaining these invariants requires you to keep some sort of nice structure on X cross Y, and periodically you're adding new coordinates, querying new ZIs to keep the structure nice. And I've described the deterministic version. For a randomized algorithm, you need a stronger extractor-like property that these are essentially equally likely. So anyway, that's the general framework. And so what does it mean to be nice? What is the structure on X cross Y that's nice? The original one in Roz Mackenzie had average degree, which is known to be limited to linear size gadgets. And I'm not going to define them here exactly, but there's deficiency, which is how many fewer inputs do you have than are possible, or min entropy rate. But anyway, with this, the current best gadget sizes are, let's say, that the number of bits for the Y player is like n log n in this paper from ToniCS 2022 with Ian and Toni. So good, Ian's introducing us, and it's based on an improved on the improved sunflower lemma. Now, as you know, even reducing this M to polylog n for index would lead to breakthrough results. But again, well, at least Tony's always looking for the ambitious thing. So constant size gadgets should be the what we should be aiming for. And actually, in the paper, there was a conjecture that if you were any m larger than a fixed constant, has good disperser property for any sets of Bob's inputs with small deficiency. In other words, the size of these sets is close to the maximum possible. And this is where Sajin and I were inspired to think about the question, and was a really nice collaboration during the pandemic. And the first thing we realized is that for somewhat silly reasons, in some sense, all zero blocks, the above conjecture can't be true either using small deficiency or large min entropy, which are the two other existing things. If that's all you use about the sets X and Y, then you can't get this. Now, of course, m less than log n is a big gap from n log n, but it's also true for the inner product function, where we can prove this for something, I don't know, 5, 10, 20 log n, I'm not quite sure. So the same thing holds. We can't get the size of inner product gadgets if all you're going to use is deficiency or even large min entropy, which is actually what is used to prove the lower bound for the inner product is the large min entropy. So that was the first thing. And well, maybe the conjecture, this specific version isn't the right thing, but what other condition, yeah.
Can you say a few words about silly reasons?
Okay, so here's a silly reason. So in a random input, you've got m blocks, right? In m blocks, how they've got probability 1 over, if they're smaller than log n, you would expect about they're little n blocks, you're going to expect a reasonable chunk of all zero blocks in the input y. And there's nothing about the inputs x that will ever get you both values. Yeah.
Could we fix this by restricting in advance to y being like an error correcting code?
So there are various things like that are that kind of thing is exactly the sort of thing that might be able. So I'm more optimistic maybe than Toni now, but something like that balance error correcting code, something of this sort does seem possible. And of course, we're talking a constant number of bits, but we can pick big constants. So I think it's not out of the question. Polylog would be, any of these would be great. Yes, absolutely. We tried, we weren't able to do that. So at some point, we even thought we could prove something, above, but didn't work out. So we weren't quite sure what that could be. So the next thing we did was say, first to try a restricted class of protocols. So maybe we could prove it for a restricted class of protocols that would give us some ideas. And this is the other part of our work is that for restricted protocols, lifting with constant size index gadgets is possible. And this is the class that for whatever reason we decided to try. So in our restricted protocols, there's no limit on what Alice can send, but Bob, who has the long string Y, can only communicate parities of input. So we've got a star to say that Alice can send anything, and that's not multiplication, but it's and parities for Y. So that's the That's the restricted class of protocols. And it turns out we can indeed prove, even with, Alice has 2 bits and Bob has 4, that you can actually get a full lifting from decision tree complexity to communication complexity. And then we realized actually that if we made Alice send bits, we could actually do some nice things to balance the size, and similar ideas would do things for decision tree complexity and decision tree size. And there's a version for relations that gives proof complexity lifting from tree res to tree res parity. I mean, Dmitry Sokolov and Itzikson had shown specific examples based on actually one of the, Pigeonhole and the Titan lifting that I mentioned that's in the Lovis driver and beyond. But this gives a general family. And then, as Suhail was mentioning last week when Sajin was presenting this at Banff, we discovered that this was actually independently known. So if you were in the talk last week, Suhail talked about this result. And the proofs are very, very similar. The key ideas are very, very similar. So I'm just going to give a little bit of the base. Oh, yes. So here's the overview of the simulation. We've got some invariants. We're going to make sure Y is an affine subspace of the set of index vectors. And the codimension of that space is going to be at most the number of bits sent so far. And the simulation maintains a set of dependent coordinates, Yij, and all other coordinates are free and can take all possible values. The set X has high min entropy rate, and this means that no value has too large a projection. So there's our definition of high min entropy rate. And the other thing, no coordinate that's outside of the set I, where we've settled everything, points to a dependent coordinate of Y. So those are the invariants that we maintain. The actual proof, again, if you were in Suhail's talk last week, you can almost guess what's going on. So here we have a node where Bob sends some parity. And let's suppose, there's a 0-1 possibility. So let's suppose we're going to go along the 1 path. The simulation here actually, maybe the other path is even possible, but in this case, the simulation actually has a choice. But anyway, so we add the equation, rewrite this. So we're going along this path. Y11 is 1 plus Y34, and we choose this arbitrarily, and we mark that as a dependent coordinate. Then we update X to remove that dependent coordinate. So we add this constraint. And then Bob maybe sends some other thing, and notice Y11 is also in that one. Again, we have possibility. Let's pretend we're going to follow the 0 branch. So we're going to rewrite this in a way. So Y11 is dependent already, so we're not going to choose that as a variable. So we pick Y43. We put that on the other side. Again, we make sure X doesn't point there. Now this may lose min entropy rate down here on the X's. What happens if Alice speaks again, 0 or 1, you pick the side that's more popular. If it's parities, you get a choice. You just restrict to the set of inputs. It may lose min entropy rate. So we got 2 things. How do we handle it? Well, we go to Toni and we use the density restoration method of Pitassi and Watson, which actually is the part that makes the queries. And we do the same when of course, when we were in the previous step, if it happened to lose min entropy rate there. And that's basically it. That's essentially the whole proof. Yeah.
What happens in the DAG case?
What happens in the DAG case? Well, you will notice we've been maintaining dependent coordinates, and now we decide, and we got 2 paths that come together. We've got completely different set of dependent coordinates, and we have no idea about how to proceed because we've been basically keeping track of the entire history through this process. And it's a little unclear how you would, or not a little, more than a little unclear how you would combine these. So yeah, for those of you who aren't paying attention, what about dependent coordinates is basically the open question here, which is DAG-like, so DAG-like lifting protocols for parity, right? That would, if we could handle that, that would solve, that would give us resolute lower bounds. That would be amazing. There are, what are these other conditions? I think this is actually really right. We have to get our mindset to things like, Eric Crichton codes, as Russell said, or some sort of something that will do this. And maybe other restricted class of protocols will give us new ideas. We tried that. I'm not so sure, but anyway, this is like for the general case. Of course, the DAG-like case would be good. Yeah, Russell.
Please generalize to protocols that use other symmetric functions, or
so majority threshold is the next thing we tried, and it gets pretty tough. The parities interact in really nice ways. A collection of majority constraints is a very complicated object. So, but we definitely tried some of that. I'm not saying it can't work. That was, in fact, in Sajin's slides at ITCS, he actually mentioned that, but as one of the possible directions for doing this. Yeah. No, it's.
Do you have a matrix that you can somehow do it to make it somehow? Why are these sets nice? Isn't that why?
It could be. So the question is, is it because we have a matroid? That's certainly possible. I mean, the other thing that's nice. I mean, one thing that's nice, we get to pick what the basis is, and of course, the matroid you do get to move bases around, and that's another kind of thing. I'm not quite sure on the restrictions itself, but if you actually work through, it's so straightforward in some sense how the proof works. I hesitate to say that it's only matroid properties that we're using. So because I just haven't thought so much. So anyway, finally, Toni, you've been completely inspirational for me, for my career, hey, in my life. Most of all, on all of these things, most of all, you've been a true friend. Thank you and happy birthday.
Thank you so much.
Yeah, this is maybe totally out there. But I don't even know if I want this on film. No, this might be totally out there, but the new AP result. I wonder if some of those ideas could be used to.
So
anyways, this is just a throw out.
So I just missed the arithmetic, the three-term arithmetic progression.
Like they have these two notions, one that they want, and then the other one they want to morph it to be a subspace, like parity, and they a bunch of tools that I don't think have been explored well.
Yeah, I mean, it's certainly that's super exciting work. It's something I want to understand better. I don't have a clue whether it connects, but it's yeah, it's definitely very exciting. Yeah, sure.
Other questions?
Yeah. So probably the time for a lifting primer.
A lifting primer. Oh, well, there's Toni has already written most of that lifting primer. Well, or Mika. Anyway, so yes, it probably is time for a lifting primer for sure.
You just volunteered to write it.
Yeah.
Other questions? I'll ask. So I am also kind of optimistic about that counterexample. I guess it's exactly the same one as the sunflower lemma counterexample, actually. It's like a blockwise set system where you just take basically every set, which is like a full X, and then Y, you just like take half of them.
Yeah.
So, but yeah, it seems like there's a lot you could do inside that, stick to error correcting code or whatnot. If that's not true, do you think that we could use that counterexample to exhibit? Do you think it's so natural? Do you think it could relate to some specific communication problem, lifted communication problem that actually can get gains when you put the size too low?
That,
So what's the end of the question?
so if it's not a general lifting thing and it fails, somehow can we get a communication, like would that could we convert that to figuring out what the hard problem is for lifting? That would actually, I mean, right, this I mean, basically this win-win thing, I think is a great strategy for working on problems, to try to solve, so yeah.
Yeah, I'm only asking because your counterexample, yeah, it's for silly reasons, quote unquote, but it's also so like you could imagine it arising in practice, like so simple, right?
Yeah, I mean, more generally, we don't really have bad examples for lifting.
Yeah, right, yeah.
Right, yeah, good. Okay, other questions? Sorry, the mic's on. All right, well, let's thank Paul again.